Okay, today we're going to talk about conservation of energy. So conservation of energy says that energy cannot be created or destroyed. For us, that means that if a system is isolated, which is most of the cases, the energy before is going to equal the energy afterwards. Or if a system gains or loses energy, if we know that the system is going to gain or lose energy, that means work is done. So essentially, what this means is that whatever our energy total beforehand is going to equal our energy total afterwards. Except for the case when work is done, and the only case in our course when work is going to be done in an energy problem, in a conservation energy problem, is going to be when there's friction. And so in those cases, the energy before is going to equal the energy afterwards. I should do final, actually. Energy final plus whatever the work is done. So whatever energy was lost will add to the final side. Okay, so let's see what that looks like. If we have a boulder that's falling off a cliff, what's the final velocity? Well, in this case, again, we can think about whatever our energy beforehand is going to equal our energy afterwards, right? I always write it weird. Imagine that's an E. Great. Energy before equals energy afterwards. What is our energy before? Well, beforehand, we only have potential energy, right? We're on top of a cliff. Anytime you see a height, you should associate that with potential energy and gravitational potential energy specifically. So we have UG beforehand. Afterwards, we have a velocity. If you ever see a velocity, if you ever see an object moving or have an object moving, you should think about it being kinetic energy. So afterwards, we have kinetic energy. And we know that energy is conserved, therefore the energies are equal. Our potential before must equal our kinetic afterwards. So mgh equals 1/2 mv squared. So that 50 times 9.8 times our height of 35 is equal to 1/2 times our mass times our velocity squared. Let me go grab a calculator real fast. $50 times 9.8 times 35. 50 times 9.8 times 35 is 17,150. And then 1/2 of 50 is 25 v squared. Let's divide both sides by 25. We get 686 equals v squared. And of course, we need to square root that to get our final answer. And we get 26.2 meters per second. Let's say we have a spring with a K constant, 5,200, on the ground that launches a ball straight up into the air, and the ball is launched 327 meters. How much was the spring compressed? Well, again, energy before equals energy afterwards. So energy before, what kind of energy do we have at the beginning of the situation? Well, at the beginning, we're on a spring, so we have spring energy. Afterwards, we're launching a ball, and we launch to a height of 327. We're assuming that's the max height it's going to go. Therefore, we're assuming that afterwards we have no kinetic energy, we only have potential. Because remember, from kinematics, when we have a ball at the very top of its motion, at the very top, v equals 0. And we know that because if it's going up and back down, on the way up we have a positive velocity, on the way down we have a negative velocity. Therefore, at the top we must have 0. So, 1/2 kx squared equals mgh. And all we have to do is, again, plug in our numbers here. Once we do this, the physics is over. After that, it's just math. You plug in your equations, and then you plug in your numbers. This should be an x squared, my bad. 298, 327. Just plug in your numbers and solve. So 1/2 of that is 26 x squared. And then 2 times 9.8 times 327. We get a big number. And then we divide that. And we get x squared is equal to 2.465. And then we take the square root to get our x, and we get x is equal to 1.57 meters. Lastly, we have a box on a ramp. I'll draw the situation. We have a box. Let's say it's a box on a ramp, and it's going to go down the ramp, and then it's going to slide across the floor. On the ramp, we have no friction, but on the floor, we do have friction. Okay. So the question is, what is the force of friction on the floor? Well, let's think about this. What energy do we have at the beginning? Energy initial equals energy afterwards. And in this case, because we have friction, anytime you see friction in these kinds of problems where we have heights and energy problems, you should also be thinking that we're going to do some sort of work, because work is going to be done by friction. So energy beforehand. At the beginning, we just have potential gravity. At the very beginning, we just have a height. We have a height of, 3 meters? We have just potential energy of gravity. Afterwards, we go down the ramp, so we lose our height. No more height. Height equals 0 now. And then afterwards, at the very end, we actually come to rest. There is a time where we have velocity, right? At the very bottom of this ramp, we're going to have some speed. But at the very end, we have v equals 0. So we have no kinetic energy afterwards. So we have no energy afterwards. All we have is work. All the energy went into work done by friction. Okay? And so mgh is equal to the frictional force times delta x times cosine theta. We're just plug in the equation for work, and in this case, it work done by friction. So plug in the equation for work and friction. And then we're just plugging in numbers at this point. Height is 3. Frictional force, what we're looking for, we are going to go 21 meters. And then cosine, well, what's our angle? Again, anytime we have one angle with some forces, let's do a free body diagram. The frictional force is to the left, and our displacement is to the right. Therefore, it's 180. So 9 times 9.8, 88.2 equals frictional force times negative 21. So let's divide by negative 21, and we get frictional force is equal to negative 4.2, which makes sense that it's negative because it's the frictional force is to the left. And that's it. I went through really fast. You just have to do the problems, do the practice problems. There's a lot of conservation of energy problems out there on too. So if you go to like physics classroom will have they'll have some basic energy problems. I don't know if they get into springs or not, but they'll have some simple ones. That might be a good place if you're confused. Go there, check out physics classroom conservation of energy examples, and they'll have a bunch of worked out examples for you to just kind of go through the process of setting these equations up, and it'll help you out a bit. Okay. Once you get that, once you get the idea, you can add springs in. I think springs are actually the easiest because they're pretty obvious if there's a spring or not. It's all the kinetic energy and potential energy, the things that get confusing, especially with questions where on like the first example, let me work it out. The first example the first question on the homework, part B, it says, hey, what's the velocity halfway up? Well, velocity halfway up, we're going to have both kinetic energy and potential energy, right? Because halfway up in the motion of a ball, right here, we both have height, but we're also still moving. Okay, so we still have velocity and h. Therefore, we have to have both. And so it can get kind of confusing. You need to do the practice, and then you need to look at examples. And so you can come to tutorials and I can help you out with these, but you can also just look on Physics Classroom, and they have really good worked out problems. If you need a link for that, you can email me. I can try to send you a direct link to the examples that they have there. With that, I am out.